All right, we are into our next unit, which deals with energy and work and power. So we're going to start with the concepts of work and power, and we're trying to kind of see what work does. So it's a very useful process. So work is done on a system by external forces. So like there are forces. We just got done our unit on forces, and those forces are applied to objects, and they do work on those objects. So once we learn about energy, work is the transfer of energy from one object into another. So it's like taking energy out of one thing and putting it into another thing. But if we're just talking about it in terms of forces, it's a force acting on something that causes a displacement. So if we look at this example here, there's it looks like a sailboarder, and there's a force of the wind pushing on the sailboarder here, and it moves it from this place to this place. So that is a displacement, and it's that process of the force acting over a displacement or causing a displacement. So the basic equation for it, the most simple equation, W equals FD, where F is some constant force and D is the displacement that it is going through. The unit for work is the same as the unit for energy, and we're going to call that a joule or a Newton meter, which makes sense because a Newton is force and a meter is the displacement concept. So let's go ahead and jump into a problem. So it says a dog and a weighted pulling competition tugs on a sled 4.9 meters across a snowy track at a constant speed. The force needed to keep the sled moving is 350 newtons. How much work does the dog do? And where does this energy go? So essentially, we're going to not worry about the energy part because we haven't talked about energy yet, but we're trying to find out how much work this dog is going to do. So you got to look at kind of the situation of what's happening. So this dog is pulling on this sled. So this is a sketch that I got out of a book. But so the force would be like the force of tension. Usually I write an F here, which is fine. So it would be the force of tension is pulling on the box. And that tension force is going to act over that displacement, and it's going to move the box. So we have that. And really, if we drew a free body diagram, we'd have the force of friction going the other way. And they are balanced because you know that because it's going at a constant speed or a constant velocity. So friction would do the same amount of work just in the opposite direction, being negative. And this one you get positive 1715 joules when you multiply the force of the dog, which is pulling with 350 newtons, and you're multiplying that by 4.9, which is the displacement. You get that value. So that is the idea. That is just basically what you do. Sometimes work gets a little more complicated when there's angles involved, but for right now, we're just talking about a very basic idea of positive work. So as I mentioned, getting to the angle part, when there is an angle, so not all forces and displacements, so if this is my displacement here, the direction that it's moving, the change in position, and the force, if they aren't going exactly the same direction or parallel to each other, so those two lines are parallel, then you have to use a trig function, which is the cosine of the angle, to figure out how much or what portion of the force is actually going in parallel. So you just worry about the parts that are going parallel. That's what this notation means. And to do that, you do the force times the displacement times the cosine of the angle between those two ideas. So if you look at this picture here, there's a force going up and to the right. The displacement of this person is going that way. So you need that angle between them. So this angle here is what we would measure as theta. And that's what it's showing here. So we really just care about kind of if we do the cosine, that's the x portion here in this triangle. So it would be how big that portion is in the x. That's what the parallel part is, and that's going parallel to the displacement. We don't care about that vertical part. The perpendicular part is going to do no work. All right, because if you think about it, like the only part the part of the wind that's pulling on this parachute that's pulling it to the right, that's the part that is doing work. The part of the parachute that's trying to pull up on the sled like that isn't doing any work because it's not going. This force up is not in the direction of the displacement. So work is always just how these agree. So we're talking about agreement and the parallel nature of them. Okay, so this slide, and it's over a couple slides in your notes, but I've kind of condensed it onto one page to talk about it all at once. So in this one, you have kind of the most basic situation where the the force, which is in red here, is in the same direction as the displacement. So that's just FD. You could say cosine of 0, because that's the angle between them. So to talk about the angles, so if we draw out our x and y axes, and when you line up the force, so the force is in red, so if I draw the arrow in red going to the right, and then the displacement was in blue here, so if I have that displacement going the same way, so we got the displacement and the force, they're going the same exact direction. There is no angle between them, so that theta would be 0 in that case. That I could rotate this any way, so whoops, that's not what I was trying to do. Do that back. There we go. I just want to grab that. Okay. I'll group that together, and I could rotate this any direction. So like those force and displacement arrows are still going the same way, so their angle between them would be 0. So it's not about physically where it goes, like it doesn't have to go to the right to be at 0 degrees. It's talking about how the force and the displacement either agree or disagree. Okay, so in this case, the force is the red still arrow. It's going up and to the right. That's along like the rope or the tension. And then the displacement is still going to the right. So this angle is less than 90 degrees, but it's still going to get you positive work because there's agreement. So you get a positive value. So like the part of the red vector that goes to the right, which we drew kind of in the other one. So that is like Fx, or the force that is parallel, they use parallel here, to the displacement. So again, those are agreement, so you get a positive value for work. When the force vector, which is the red arrow here, and the blue displacement vector are perpendicular to each other, so you can see that like this force here is perpendicular to the displacement, that angle is 90, and that makes sense too. So if I come back over here and erase a little bit, so if I draw those arrows back in for the x and y, so I could have a force that is directed, say, I don't know, down. So the force vector is pointing down, and my object is moving to the right. So I have the displacement vector to the right. That angle is 90 degrees. There's 90 degrees between them, so that would be 90 now. And if you put cosine of 90, you get 0. So this force is doing no work. So that's like a really easy way that you can identify forces that aren't doing work and maybe eliminate them. So if you see that they are perpendicular, the force and the displacement are perpendicular, then you don't have to worry about calculating that amount of work. For all the other forces that are the angles greater than 90, so if you look at this, this is the angle here between the displacement and the force vector. That's theta here. If that angle is greater than 90, then you're going to get negative work, because when you put in an angle that is greater than 90, you get negative work. So if you were at 180 degrees, like in this one, so let's say this box was like sliding to the right, but friction was going to the left, so they're 180 degrees away. If you put a cosine of 180 in your calculator, you get -1, so you'll get negative work. So the way that I like to think about this is that if you have positive work, you're adding energy, and we haven't talked about energy, but I think most people have a conception of energy already. So you're giving like you're putting energy into that object, and that should be a capital W for work. And if you have negative work, you are removing energy. So like the idea about friction slows things down, so that would be taking energy away. If I had a situation where I was pushing something, I would be adding energy because it would start to speed up. So that's kind of a connection back to energy, which we're going to learn about later, and we'll talk about something called the work energy theorem. All right, so let's try this one and decide what kind of work is being done. So it says a crane lowers a girder, which is just like a bar. So it's one of those big, long metal beams. So if that's it, and there's the crane with the hook on the crane or something, I don't know. I'm not a very good artist, like you said. But you get the idea. So a crane lowers a girder into a place at a constant speed. So the velocity is going down. So the displacement is also going down. And we're trying to figure out what's the work done by gravity and what's the work done by the tension. And really, we're just deciding whether it's positive or negative. So if we think about this, which way does gravity always pull? Gravity always pulls down. So Fg is going down, and then that tension in the cable is actually going to go up. So I'm going to draw that going up. I'll label that FT. And again, for both of these, we're not really we don't have any numbers to calculate the actual work, but we can look at kind of whether they agree or disagree. So this directional arrow for the velocity displacement is pointing down. Gravity points in the same direction. So gravity is going to be positive. The work done by gravity is positive. In terms of mathematical sense, that means it's greater than 0. So C and D and E aren't going to do anything. And then for the tension, for this one, tension is pushing or pulling up and the object's moving down. So they are at 180 degrees. So if you do that, they disagree and you're going to do negative work. So the tension is slowing it down. That would be less than 0 in mathematical terms. So B here is the correct answer because that's not right for that piece. All right. So let's try another one. So it says Robert pushes the box to the left at constant speed. In doing so, Robert does what kind of work on the box? So again, this is Robert. He's pushing, it looks like, to the left. So we'll say the force of the push is going to the left. The box is moving to the left at a constant speed. So the displacement is also going the same direction. So that's going to be positive work. They're in agreement with each other. To make it go at a constant speed, we'd have to have the friction force going against that, and that friction force would be balancing out the push force. So like that force and that force would be balanced. Friction, the work done by friction would be negative, and that makes sense because friction always slows things down. But Robert's pushing force is going to be positive. So again, I think if you just kind of think about how they line up, so if you think about the force and the displacement, and if they agree or disagree, that's what makes it positive or negative. All right, this one's a little trickier, so let's try this one. So it says a constant force of F, and that's in red, pushes a particle through a displacement of delta R. So delta R, that's your displacement concept. In which of these cases does the force do negative work? And you have choice A, B, C, or D and E. So let me give you a second to think about that. So again, what I try to do is think about, okay, well, how do those arrows line up? So C is the easiest one, I think, to look at. So if we look at C, C is going to have positive work for C because the force is going the same direction as the displacement. In A and B, I would say that they are going in opposite directions. So F is going to the right in A, and then the displacement's going up and to the left. So like they're disagreeing in terms of their kind of motion, and same with B, it's just flipped over. So the correct answer is D here, that A and B are both going to do negative work because the force vector and the part of the displacement that it's lined up with, that's got like, they are going in opposite directions, and that just flips over for situation B. So, yep, hopefully you can see that. All right, so let's try a problem ourselves with work. So it says a person pulls a 50 kilogram crate 40 meters along the floor at a constant force of 100 newtons at an angle of 37 degrees above the horizontal. There's a 50 Newton friction force that acts on it as it slides. Draw a free body diagram for the crate, determine the work done by each force acting on the crate, and then determine the net work done on the crate. So net work would be from the net force, so we'll get to that in a second. So just reading through this, 50 kilograms, that's our mass. 40 meters, that's going to be our displacement. 100 at 37, that's like the constant pulling force, so I'll call that F pull. And it says friction is there as well, so this 50 newtons is the force of friction. Hopefully you can see how a free body diagram would be important to this because it's going to draw the arrows in the directions that you would think they would go. So if we think about this, we got a pull to the right, we got friction to the left. I'm sorry, the pull is up and to the right because it says 37 degrees above the horizontal, so it's pulling up and to the right. We have gravity acting on this crate, so that's going to go straight down, and it's touching the floor, so the floor is pushing back up on it. So this is what I would say the free body diagram should look like. So pull going up and to the right, normal force is going up, gravity is going down, friction is going to the left. Remember, this pulling force has components, so it's got a part that is going to the right here, and it's got a part that's going up. Hopefully I drew this in well, but I might have shorted this gravity. The gravity should be bigger than the normal force because these two are adding together to get to that. But that's more of a force concept, but I just want to make sure we say things properly. So figuring this out, we can look at kind of the forces that are acting and what we're going to do for each one of those forces to determine the work done. So looking at this picture is going to be helpful. I'm going to take another snippet of it and bring it to the next page because it's easier than flipping back and forth. All right, so here we go to the next page, and let me shrink this a little bit. So so having this picture is going to be useful to just keep a visual eye on to determine whether something's positive, negative, or zero. And if you recognize the ones that are perpendicular, those are the zero ones, they're easy to talk about. Just looking at this, so our pulling force is going up and to the right. Our object, and I drew this red arrow or this red displacement going to the right. So the pull is going the same way as the displacement, so that's going to be positive. Friction's going against it, so that's going to be negative. And then for the normal force and the gravity, they are both perpendicular, so they're not really doing anything. So you're just going to plug into the work equation, which is, again, W equals FD cosine theta. And then the angle you just can figure out from the picture. And when they're parallel or anti-parallel, you don't have to worry about the cosine part so much, but when it's at an angle, you do. So F pull D cosine theta, so 100 is the pulling force, 40 was the number of newtons, cosine of the angle 37, and I rounded this slightly, but 3,195 is pretty close to the amount of joules that is there. And that's a positive because, again, this green arrow, the x component of the pulling force is going the same direction as that displacement. For the friction, I'm not sure if I did friction next, I might have done gravity next. I did the normal force next. The normal force, we don't know the number, and we don't really have to solve for it. It's okay. You don't need to do that. But we know the displacement's still 40. This time the cosine's 90, so that's going to get you 0, so you don't have to worry about that. For gravity, same thing. We could do the gravity calculation, so 50 times 9.8 times 40. I did 270. You could do it that way, or you could just say it's 90 again, but it goes to 0. And then finally for the friction, it's the friction force, which is 50. Times the displacement, which is 40, times the cosine of 180, and that gets you negative 2,000. So we have all these works being done. And how do you think we're going to get the net work? So just like the net force or whatever, you just add. So it's like 3195 plus a negative 2,000. These are both zeros. So you're going to get 1195 to get to the net work. If you calculated the net force, you could have done that as well. So if you did 100 times the cosine of 37 minus 50, and then multiplied it by 40, you would get the right answer. So it works out that way too. So there's just a quick going through an example with all these different forces and displacements and finding the work for each one. So this is another thing that sometimes people get confused on because the physics definition of work is not the same as like your everyday language use of the word work. So sometimes there is no work being done. So if an object doesn't get displaced, there is no work. So in this example here, they have a weightlifter holding, it looks like a barbell over their head. And obviously that's going to be difficult. Like you're going to feel like you're doing work if you're holding a barbell above your head for an extended period of time. Because you're applying a force, but the displacement's 0. So technically, in definition terms of physics, we don't have any work done there. Another one is where like that force is perpendicular to displacement. So this thing is getting displaced now, but that force that you're applying, that force that you're using to hold it up, isn't doing any work on it. So sometimes the physics definition versus the real life feeling isn't exactly the same. Okay. So let's try another kind of example. So it says, I swing a ball around my head at a constant speed in a circle with a circumference of 3 meters. What is the work done on the ball by the 10 Newton tension force in the string during 1 revolution of the ball? So if I had a circle here for the ball, and I have it connected to a string, and it's going to go around in a circle 1 complete time. So if we go around in the circle, what's the work done? Well, you might have an inclination to say, oh, I have 10 newtons of force and I need to figure out like the radius or the circumference of this circle Circumference is the circle is 3. I thought it was the radius. I misread. And you might say, oh, it's 30, but that is not correct. Okay, because again, we don't worry about the distance traveled. We worry about the displacement. So this ball started. The initial position of the ball is right there. That is equal to the final position of the ball. So our change in position is actually 0. And if we plug into the work equation where it's FD cosine theta, in this equation, D is displacement. So if that is our displacement is 0, that means this whole thing goes to 0. So if you start and stop at the same point, there is no change in energy, or there is no work being done on that object. All right. So the last idea we're going to talk about today is power. Power is just the rate at which work is done. So you're going to basically calculate the work and then divide it by how much time goes by. The unit for power is a watt, and that's a little confusing because it's a capital W. Light bulbs are measured in watts, microwaves are measured in watts, so it's talking about how quickly you're doing the work. If we had energy here, we could replace work for energy. It's how quickly you're using energy. So like if you had a 10 watt light bulb versus a 100 watt light bulb, obviously the 100 watt is more powerful, and the way you can tell that is it's brighter. The brightness is talking about how much energy it's using per second, or how much light work it would be doing per second. So it's doing more work per second, or a watt is again a joule per second. So just kind of a real life thing, right? Sometimes it's easier to use this equation to calculate power. So this is just the derivation of it. So if you have power equals work divided by time, work again would be force times the displacement. Delta x could be the displacement if it's horizontal, or you could just replace that with a d. But you could take and group those together, where the displacement divided by the time, that's a velocity. So this is another way that you could calculate power. All right, so let's try one more problem and then we're about done. So it says a 200 Newton pushing force acts at 15 degrees above the horizontal to move a box to the right 10 meters in half a minute. What amount of work is done by the pushing force? How much power is required to perform this task? And then how much power would be required to perform the task in 15 seconds? So 200 Newtons at 15 degrees above, that's F push. 10 meters is the displacement. And then half a minute, we don't work in minutes, so that's going to be our time, or change in time, or time period. And that's just 30 seconds, so we can write out 30 seconds there. Okay. To get the work, it's just the work equation, so FD cosine theta. We're assuming that goes the same way. We've got an angle, so it would be FD cosine theta, so it would be 200 times 10 times cosine of 15. You get 1932 for that. Again, probably a little rounded, but I just rounded to the whole number. And then to figure out the power, you just take that work and divide it by time. So we're going to divide that by 30, you get 64.4. Finally, you're asked to calculate how much power would be required to do the task in 15 seconds. So you take that same amount of work and divide it by 15. That's half the time. Thinking about proportionality, if you lessen the time, the power will get greater because they're in opposite parts of the fraction. They're indirectly related. So so we cut it in half here. So this is going to double. So it's actually 128.8 when you do that in your calculator. An example from kind of using your body, a weightlifter performing a move called a clean and jerk. Lifts a 190 kilogram bar from the ground to a height of 1.9 meters in 1.8 seconds. Again, the power output is what we're looking to find. Don't worry about all this. It says a lot of stuff. And it talks about energy, but we're not worried about energy yet. So going through this example, the work again is going to be FD cosine theta. So they're overcoming the force of gravity to lift something, and the displacement is D. So mg, which would be 190 times 9.8. D is the 1.9 meters. So when you do that, they do 3,538 joules of work. So we're going to try to solve for the power, and we're going to divide that by the 1.8 seconds. Oh, I just got to scroll down. So if we take that 3538 and divide it by 1.8, you get 1966 watts. So that's a lot of power. It's a very powerful move. 2.6 horsepower. That's what it turns out to be close to. Horsepower, like in your car, is just it's just a different unit for the way power is measured. So just a summary of the two ideas. So work is the process in which energy is transferred to or from a mechanical process. Again, the way that we are learning it right now, so it deals with energy, but when you do work, force, when a force causes a displacement, or when a force is acting against a displacement. It's that parallel part of the force. So if this is the angled overall force, we just care about this parallel part. That's the only part that does work. The perpendicular part does no work. And you can do a positive work if it agrees, and if it goes the opposite way, it disagrees, and in a way, then that's negative work. And then finally for power is just the rate at which work is done. You just take W, the amount of work that you've done, and divide it by how much time was required to do that job. Okay, so I finished up. It's about 25 minutes in, so that's good length. I will stop there. Have a great day. Be well. I'll talk to you later.